I was just stressed out about it.
You forgot the transmission line. It's in my office at Sean's office.
Yes.
I left it in the office.
Yes.
Okay. So, questions? This is odd. Usually I get, before any quiz, especially for a review session for tests, I get a lot of questions. Yes?
What's going to be on the midterm?
What have we done for the last 5 weeks? Somebody asked about equations. Let me just clear the air on this. You're going to get the input impedance for a transmission line. That's Zn equals Z naught times ZL plus J Z naught tangent beta L over Z naught plus J. You're not my class.
Watch.
Or you can hang out if you want. Didn't you have this one?
Yeah.
I'm seeing things sometimes. Anyway, one of these, you're welcome. Anyway, you're going to get that equation. Y'all follow me? Now, most of the equations you should know just because of use. I'll give you the curls and the divergence, the Laplacian, and the gradient, and I'll give them to you in Cartesian, cylindrical, and spherical. So you're going to get all those if that's the concern. And you'll have that, but I mean, you have to know the basics yourself. I'm not going to, I'll give you mu naught, I'll give you epsilon naught. If there's a conductivity for copper, I'll give it to you. I'm not going to expect you to know those things. The speed of light you should know, but I'll even put it down to 3 times 38 meters per second. In other words, I'll give you everything you should normally would get on a quiz will be provided on the exam. And he's had me before. You can ask him anything you are curious about. He'll tell you exactly what I'm like. In a nutshell, if you know how to do the quizzes and the homeworks, you're really know how to do it, you're very prepared for the exam. What?
True.
True. The only thing I will say is please don't just memorize, oh, that's the solution for a spherical, or that's the solution for, because I'll give you different permittivities or different conductivities, so the answers will not be the same. In other words, if there are functions of distance, they won't be the same. You'll follow me, class? I'm just trying to level you. Now, did you have a question back? Oh, you're just okay. What I'd like to do, I was doing boundary conditions last time. I was finishing it, right? So I'm just, if you got a question, ask it. I was just going to finish that last thing on boundary conditions. And then we'll go ahead, maybe do one problem on it. Then if something occurs you'd like me to do, I'll do it. Then we'll get to the quiz, okay? Yeah.
How many questions are going to be on?
I get that all the time. There are going to be 4 problem statements. Basically, 4 pages with different multiple parts. Now, yes.
Are you going to have a review session?
This is it. Test is on Monday, right? Okay, this is it. We don't have another class period between now and the test. There's one in every class. Anyway, you were in that class, so I'll just say this. We all agreed to move a final exam. Oh my God. Unanimous. And I even got permission to do it. Usually I don't try to bother my department chair because he gets a little ticked off now he's got to make sure it's okay with the administration. So I get okay to do it. Then a day or 2 before I get a message, oh, I need much more time to study. And the guy voted on changing the final exam. So I had to get everybody to vote again to have the exam on the same day. If you vote on an exam day, unless there's an earthquake or a hurricane or something of that order of magnitude, that's the day you're going to get it. Follow me? And but I remember that. I never had any annoying. After everything I did, the guy said, I want the regular. So anyway, now we're going to go through boundary conditions, all right? I'm going to ask you a question. The first boundary condition if I have media 1 and media 2 here, and I have an E field in media 1 and an E field in media 2, and I'm going to just try to make sure these are somewhat the same. So this is E2 here, total length. There's two conditions that we talked about. The first had to do with the tangent electric field. So if you took the projection of this vector E1 tan here, it has to be equal to the projection of this vector E2 tan. Y'all follow me? Tangent electric fields at the interface of any two media have to be the same. It doesn't matter if they're conductors, or I should say for dielectrics, conductivity of any type. That has to be true. The second thing is if you have two media right here, and you have two electric fields. And I'm going to do one other thing too. I'm going to say at this interface, if the surface charge density is 0, so we have no charge layer at the surface, then if you have a D field, I mean the E field obviously is a scalar of the D field. If you have a D field here and a D field here, what you'll find is the normal component, this would be the normal component right here. D normal in region 1 will be equal to D normal in region 2. Now that is if there's no charge density in the regions. Do you all follow me on that? Now those are primarily the dominant things you run into. So it's straightforward to get that if you have no bound charge density. However, if there is a charge density, and he does this in his book pretty well, and this is region 1, and this is region 2. Then if you have, and I'm just going to show you this, D normal in region 1 and D normal in region 2, you have to do one other thing, and this comes from Gauss's law. Remember, if we were doing Gauss's law, what we'd say is this. We'd say if you put a pillbox here of height H and area A, you know we have a D field here, D normal in region 1. We're going to have a D field here, D normal in region 2. And we're going to have a bound charge, rho s. Now I'm going to do this in a kind of a casual way. I'm not going to go through the exact mathematics. I'll put down the math you need in a second. But you know from Gauss's law, if we take the integral of the D field over the surface, over the closed surface, that has to be equal to the charge enclosed. Everybody agree with that, class? And I hope you can you see it in the back? All right, I'm just stating Gauss's law. Now, if you look at this, the D field here, just listen to me. The D field on the top part would be D normal times A. D normal 1 times A. It doesn't matter if that's pi A squared, where A would be the radius, or if it's a square block, it doesn't really matter. The D field down here is pointing, I have it pointing upward. So when you take a look at the surface vector for the actual surface S there, it would be pointing down, you get a negative sense to it. Y'all follow me? D dot ds there would be negative. Y'all follow me, class? So it'd be that minus D normal 2 times A is equal to the bound charge density, which would be just rho s times the area. And when we do this, we usually say let the limit as h goes to 0. So we make this thing infinitesimally tall so we don't have to worry about the h field actually on the outer part of that. Y'all with me, class? The label, you might say. Now, if you look at this, the a's cancel. And if there is no charge density rho s, you can see d1 is equal to d2. D normal 1 is d normal 2. Do y'all see that? But if there is charge, then you can see d1 is equal to rho s, or I should say d2 is equal to d1 minus rho s. You also follow me? Now here's the mathematically exact way to say this. And I'm going to put it here. So, if we have two regions, 1 and 2, and we have, I'll do it the way he does. We're just going to have some D field in region 1 and some D field in region 2. Well, then we have to have a normal vector, and this is called A21. The vector points from region 2 towards region 1. If you have your books there, can you tell me where this is in the book? This is going to be in his boundary conditions section. I'm not sure if it's 312 or 311, and there'll be a page number for this, but I want to just do this for you. Well, I'll put it down. So it's going to say this. If you take A21 crossed into D1 minus D2, you're going to get rho S. You'll have that somewhere in there. Do you see it anywhere?
186.
Page 186. Is this the form he has, this form? It is? Okay. There's a couple different forms. What it's really saying is, if you want the exact value, you have to get a unit vector, A21, pointing from region 2 to 1. Then you cross it into D1 minus D2, and that is the surface charge density. So if you're given surface charge density, and you know the D field in one region, you can get the D field in the other. You have 3 unknowns, basically. If you have any 2 of them, you can solve for the third. Y'all follow me, class? Yes.
And crossing it is picking out the normal?
Well, it's a cross product, so you're going to take A21 crossed into the D, right? And that's what you're going to, isn't this what it says in your book? Exactly in there, right? Just look, make sure.
And that's what it has up there.
And that's basically, what it's doing is that for a differential form. Now, what I wanted to do is this. I wanted to go through at least one problem that applies this. Just one. So if you look in your books, in that section, I mean, do you have any problem you want me to do out of this section? There's plenty of problems, but why don't we do just one? Do you have one? Look in the back. What section is that in? Unfortunately,
Section 312.
312. So look, yes.
Oh, my bad. That's not the same thing.
I want to do one problem. My book, I like. Go ahead. You just tell me. Read it.
For y is less than 0, epsilon relative 1 is equal to 4, and the
Well, hold on. All right. So let me do it this way. I'm going to call this y and this x. And so for y less than what?
y less than 0,
All right. So it's down here. And epsilon relative equals what?
epsilon relative 1 is equal to 4,
And this is region 1? Okay. Go ahead.
and E field 1 is equal to 3 ax plus 6 pi ay plus 4.
3ax plus 6 pi ay. Go ahead.
Plus 4 az.
Oh. Okay, so now, you know what? I unfortunately, I drew this thing in a way that's not going to be helpful. Let me do this. I want to just, I thought it was going to be just a 2D one, but he's got 3D. So here I'm going to put x this way, y this way, and z this way. And so he says for y less than 0, this is this region here, we have epsilon relative equal to 4, did you say?
Yes.
4. And we have E in this region, and he calls this region 1 equal to, go ahead.
3ax plus 6 pi ay plus 4 az.
Okay. And what does he want? E field in region 2?
Yeah.
And is there no rho s?
Rho s is equal to 0.25 nanocoulombs.
And where's rho s located?
At y equals 0. Yeah, at y
So-
equals 0 rho s.
what it's saying is in the xz plane at y equals 0, it has a value of rho s equals 0.1
0.25.
nanocoulombs per meter cubed. Meters squared. Fine. So he's saying on this surface, if you assume y equals 0 and you look at the xz plane, that's where rho s is. Y'all follow me? And he wants the E field in region 2, right? So work with me on this. Start with the tangent value. We know that E tan 1 in region 1 is E tan in region 2. That's given, right? So let's find the tangent value. Now it's important to be able to see this and visualize it. Take a moment and think to yourself. Region 1 is everything back here, you might say. Region 2 is everything over here, right? So what is the tangent plane? It would be the plane where rho s is, right? The xz plane. Does everybody see that? Can you all see it in the back? All right, so what's the tangent components of the electric field? Well, it would be the x and z components. Do y'all agree? Y'all see that? So the tangent components here in region 2, call it E2 tan, if you will, are going to be simply the x and z. 3ax plus 4az. We've got 2 of the 3 field components, right? Now, for the next field component, we need to use the d field, because d normal 1 and d normal 2 and the surface charge density are going to be needed. Y'all with me? So next, we have to find a unit vector that goes from region 2, this is region 2 over here, to region 1. What is this unit vector? A21. Just take a look. Which way is it pointing? Minus AY. Do you all see that, class? How many do? All right, it has to be perpendicular to that. So it's minus AY, right? Now, what do we need now? We have to take, by the way, we could go ahead and we might as well just do this. If I had this right here, I'm sorry, I put a cross product. That's a dot product. I'm sorry, let me do this right. I put a cross. This should be A21. You check me on this. Would you look at the formula? It should be dot with D norm or D1 minus D2 is equal to rho s. Do you see that? There should be a dot. I put a cross there, I believe.
Yeah, that's correct. It's on page 28.
It's a dot.
Yep.
I'm very sorry I put a cross. I was thinking multiply, but it's really a formal dot product. It has to be a vector dot, not a cross. My bad. I'm sorry. I apologize for that. All right. Now, if you look at this right here, we have A21. Do you all agree? And you know, I always do this. Not on the board usually, but I do it on my paper because as you get older, you'll see your eyes aren't as good and you'll miss little things like that. So I circle the negative sign so I don't think I scratched by accident. So I come over here, and now if you look at this, I'm just going to make mention of this how I do this. And hear me on this. You see how A21 is in the y direction, right? Or minus. That means when it dots into these vectors, only the y component matters. Do y'all follow me, class? With me on this? So I'm only going to worry about the y component here of E1. Y'all follow me? I could write the full D field in E1, but I know the dot product here and here will be 0 when I dot it with minus AY. So when I take a look at E normal in region 1, that's equal to 6 pi times AY. Do y'all agree with that? Y'all follow me? That's normal, perpendicular to the boundary. Do y'all agree with that, class? Can you see it in the far back, guys? All right, now, what is D normal in region 1? Well, it's going to be that, right? But what happens? I have to multiply that by what? D is equal to epsilon, right? Correct? So I have to multiply that by epsilon naught times epsilon relative, which is 4, AY. So that's D normal in region 1. Do y'all agree with that? Now we use this formula, and we go ahead and get the D field in region 2. Do y'all with me on this? So we take A21 or minus AY dotted into D1, which is really 6 pi times epsilon naught times 4 AY. And it's minus, really, it's going to be the D field in region 2, but it'll be the normal component, so it's really D2 in the y direction, AY, is rho s, and rho s you have as 0.25 nanocoulombs. Now I'm doing this formally, or trying to do it formally one time. If you look at this, you can see the AYs just multiply through and give you 1, right? And the minus sign here changes the order. So I can see that D2y, when I multiply through by a minus sign, AY dot AY is 1, right? But there's a minus, so it's minus this. I'm going to put a second, I have a minus sign here times a minus is a plus. So this is D2y, would be the first thing. And then it's going to be minus 6 pi times 4 epsilon naught is equal to that, which is really, I'm going to put 1/4 times 10 to the minus 9. Does everybody follow me on how I did this? I'm trying to do it slow. Y'all see it? I'm just rearranging things now. Now I need to solve for D2y. And that's going to be equal to 6 pi times 4 times epsilon naught plus 10 to the minus 9 over 4. So that's D2y. How do I get the E field if I have the D field? Divide by epsilon. What is epsilon over here? I mean, did I put that there? What's epsilon in region 2? Epsilon relative in region 2?
I think it was 5. Yeah, it's 5.
Is it 5? Is that right? Okay. So now to get the E field, if this is the D field right here, I divide this by 5 epsilon naught. Do you all agree with that? So if I divide this by 5 epsilon naught, what do you see happening? Let's see. Epsilon naughts go. That means I have 6/5 times 4 pi. The epsilon naughts go. And then I have plus, that's 10 to the minus 9 over 20 epsilon naught. And epsilon naught can be rendered as what? 1 over 36 pi times 10 to the minus 9. And I did that for a reason, because the 10 to the minus 9 will cancel. That's the reason I didn't use 8.854 times 10 to the minus 12. And what does that give you? That's going to be 24 over 5 pi plus, that's 36 over 20 pi. And that would be equal to EY in region 2. So the total field is going to be this plus whatever that is, EY2, AY. And that would be the total field there. What is this equal to, by the way? What is that? So that's 1.8 pi plus 24/5 pi. What does that come out to, plus? Anybody do this one? What's that? Is this what I'm trying to get at? Is this the answer? Anybody?
It's 20.7.
Say again?
20.7.
So EY2 is 28.73. Is that right?
20.7.
What?
20.73.
20.7. Is that the answer? Is that the answer to the book? in solution? What problem is this?
It's
It's 3.62.
Is that the answer in 3.62? I post the solutions for a reason. Do you have, anybody got it? I just need confirmer denial. He might have left a pi in there. If you divide that by pi, I bet you. Huh?
6.6.
6 points.
Yeah, if you divide by, but it's 3.62.
3.62.
Yeah, the y component is 20.7.
Okay, so it is 20.7. We got it. That's how you do that problem. Y'all hear me? Now, I'm going to level with you. If I give you a problem that has a charge density, I'll give you this. But you have to know how to use it. Y'all with me, class? All right, now, let me get to the test reviews and give you your quizzes. So, for the test review, we had transmission lines. If you would like to bring your own Smith chart, and I encourage you to do so, please do that. All right, you can bring several. I sent you a pretty darn good one you can blow up. I recommend you do that. The second thing is, with transmission lines, you know you're going to get impedance matching using a Smith chart. I'll probably ask you things like the standing wave ratio or the reflection coefficient. And you all remember also the complete circuit problem. How many do? All right, make sure you know how to do that. Some people are asking me about bounce diagrams. Will that be on the exam? You should know them, but I don't usually plan to put a bounce diagram problem on them. Not usually on the final you get something, but not on this test. Then the next thing we covered is really basic charge configurations and the electric field result. Do y'all hear me? So you're going to get something like that. And I can wrap Gauss's law into that one as well. So you're going to need Gauss's law basic charge configurations. That means line charges, spheres of charge, planes of charge, and then rings of charge. Y'all remember that? Loops. Loops of a certain charge. Then, after that, I also talked about how you find really everything to do, or everything you need to find either capacitance or resistance. Now, for both capacitance and resistance, usually there's a degree of symmetry that you need to exploit. So we will use something either cylindrically symmetric, spherically symmetric, or planar structures where you'll have to be able to figure out the capacitance and the resistance. Now that'll be 4 problems, I promise you. They won't be, it'll be based on everything we covered. Usually the problems that I see happening is people cram and they look at old tests or they'll look at the quizzes or homework and they'll memorize the solution for a type of problem. And it's usually wrong in a big way because all those are based on either the value of epsilon or sigma being constant. And I always make epsilon or sigma to be a function of space. Do you hear me on this? So you need to know how to do the problems to get the net result. Everybody with me? And I will ask the resistance either if I have a long cylinder between the ends of the cylinder or between the inner and outer radius per meter. Y'all hear me? So I never, don't assume they're always over the length of the cylinder. It could be between the inner and outer radius. It's important to appreciate that. With me on that, class? One last thing I'll tell you, and this doesn't usually work, but I've read plenty about this, and I know this is true for me personally. The best single thing you can do the day before exams is to sleep. If you don't get adequate sleep, I promise you, you're probably hurting yourself in a big way. I know stimulants are big and all that. I think I told you the story about the guy that was on, I think he was on Adderall or something. And I don't know if he stayed up all night, but he's taking the test. It was a final exam. He gave it to me. He goes, oh. I asked him, like, how'd you do it? I killed it. I got everything right. And he's telling me about Adderall. I can take this stuff and memorize everything. It's amazing. Everything was wrong. But he was absolutely, I don't mean like a little one, I mean, there was nothing right, but he was absolutely convinced he aced it. The funny thing is, you know, I mean, it's one thing to have somebody just saying that, you know, not meaning it. This kid meant it. What do you do with a guy like that? I mean, try to get some sleep. It helps. Sleep is an amazing